Here's a situation that comes up constantly. You have one matrix A, and you need to solve x equals b over and over. The matrix A stays fixed, but the right-hand side B keeps changing. Different loads, different measurements, different days. Running full elimination from scratch every single time repeats almost all of the work. Wouldn't it be lovely to do the hard part once, store it, and then reuse it cheaply? That is exactly what LU decomposition gives us. And the savings are real, not cosmetic. Doing the factorization costs about n-cubed operations, the same as one full elimination. But once you have it, every new right-hand side costs only about n squared. So for many different BS, you pay the big price once, and everything after that is cheap. The whole idea fits on one line. We split A into two triangular pieces, a lower triangular L on the left, times an upper triangular U on the right. Lower triangular means every entry above the diagonal is 0. L holds its numbers down in the bottom left corner. Upper triangular is the mirror image. Everything below the diagonal is 0. The numbers sit up in the top right. And one detail that matters. Our L always carries ones straight down its diagonal. We call that unit lower triangular. The stars underneath are the only numbers we have to find. And in a moment, you'll see exactly where they come from. Here is the beautiful part. You already know how to build both of them. It's ordinary Gaussian elimination, watched from two angles at once. Every step of elimination looks the same. To clear an entry below a pivot, you take some multiplier m and subtract m times an upper row from a lower row. The multiplier is just the entry you want to kill, divided by the pivot sitting above it. Nothing fancy. Do this all the way down, and it turns into an upper triangular matrix. That is your U. And the twist that makes L free. Instead of throwing those multipliers away, we save them. Each multiplier m used to clear position I, j gets written straight into that same slot of L. Elimination hands you both triangles in one pass. Let's factor a real matrix, showing every single number. Here is a 3 by 3. We'll run elimination on the right and record multipliers on the left until two clean triangles appear. We begin the way we always do. L starts as the identity, ones on the diagonal, zeros elsewhere, and U starts as a plain copy of A. Now, we eliminate. First pivot is the 2 in the top left. Below it sits a 4. The multiplier is 4 over 2, which is 2. So subtract 2 times row 1 from row 2. 477 minus 2 times 231 is 015. The 4 vanishes, and the multiplier 2 goes into L, position 21. Same pivot, now the 6 in the bottom row. 6 over 2 is 3. Subtract 3 times row 1 from row 3. 61822 minus 3 times 231 is 0919. The first column is now clear below the pivot, and 3 lands in L at 31. One column left. The second pivot is the one in the middle. Below it is a 9. So the multiplier is 9 over 1, just 9. Subtract 9 times row 2 from row 3. 0919 minus 9 times 015 is 00 minus 26. Everything below the diagonal is gone. And 9 slots into L at 32. And there they are. U is the upper triangle elimination produced. L is the record of the 3 multipliers, 2, 3, and 9, tucked under a diagonal of 1s. 2 triangles, 1 pass. Never take a factorization on trust. Multiply it back out. Here is L times U, and it should rebuild A exactly. Take a couple of entries. Row 2 of L against column 1 of U gives 2 times 2, which is 4, matching A's 4. Row 3 against column 3 gives 3 plus 45 minus 26, which is 22. Spot on. Do all 9 entries, and you get back to 31477 61822. Precisely A. The factorization is correct. Now the payoff. To solve Ax equals b, replace A with LU. Then split it into by naming the middle piece y. First solve Ly equals b, then solve u x equals y. Two triangular systems, each almost effortless. Let's do it with b equal to 5, 6, 7. Forward substitution. Because L is lower triangular, we start at the top row and work down. Here is Ly equals b. Row 1 is trivial. y1 equals 5. Row 2 says to y1 plus y2 equals 6. With y1 known, 10 plus y2 is 6. So y2 is minus 4. Row 3, 3y1 plus 9y2 plus y3 equals 7. That's 15 minus 36 plus y3 equals 7, giving y3 equals 28. So y is 5 minus 4, 28. Now backward substitution, because u is upper triangular, this time we start at the bottom row and climb up. Ux equals the y we just found. Bottom row, minus 26, x3 equals 28. So x3 is minus 14 over 13. Move up. x2 plus 5x3 equals minus 4 gives x2 equals 18 over 13. Top row 2x1 plus 3x2 plus x3 equals 5, which unwinds to x1 equals 25 over 26. That is the full solution. And for any new b, we'd reuse the very same L and U and just repeat these two quick solves. One honest caveat. Plain LU assumes every pivot you land on is non-zero. But look at this matrix. The top left entry is 0. There is nothing to divide by. So elimination stalls on the spot. The fix is simple. Swap the two rows to bring a non-zero number up into the pivot. When rows get swapped, we record those swaps in a permutation matrix P and factor the reordered matrix instead. That gives the general form PA equals LU. Same two-step solve, just with the rows put in a safe order first. Your turn. Here is a 2 by 2 matrix A and a vector B. Pause the video, factor A into L and U, then use forward and backward substitution to solve AX equals B. I'll walk it through when you're ready. First, the factorization. The pivot is 3, and below it is 6. So the multiplier is 6 over 3, which is 2. Subtract twice row 1 from row 2. 6, 5 minus 2 times 3, 1 is 0, 3. So L has a 2 below its diagonal of 1s, and U is 3, 1, 0, 3. That's the factorization. Now solve. Forward through Ly1 is 4. Then 8 plus y2 is 11. So y2 is 3. Backward through U, 3x2 equals 3 gives x2 equals 1, and 3x1 plus 1 equals 4 gives x1 equals 1. So x is 1, 1. If you plug it into the original A, x you get 4 and 11, exactly B. If you got that, you have genuinely got LU decomposition. Trap 1. Which diagonal is which? In this convention, L carries ones down its diagonal. The pivot values, the 2, the 1, the minus 26, belong to U, not to L. Trap 2. The sign of the multiplier. You subtract m times a row, but you store plus m in L, not minus m. Subtracting 3 times row 1 means L gets a positive 3. Trap 3. Mixing up the two solves. For Ly equals B, you go top to bottom. For Ux equals Y, you go bottom to top. Swap those directions and you'll get stuck with two unknowns at once. And trap 4. Ignoring a zero pivot. If elimination hits a 0 on the diagonal, plane A equals LU simply won't hold. You must swap rows and use PA equals LU instead. Let's lock it in. LU decomposition writes a square matrix as L times U, a lower triangle of ones and multipliers, times an upper triangle. U is exactly what standard Gaussian elimination produces, and L is simply the multipliers you used along the way, saved instead of discarded. Factor ones at the usual cost. Then for every new right-hand side, solve Ly equals B going down, and Ux equals Y coming up. 2 cheap triangular sweeps, and you're done. And if a pivot ever turns up 0, reach for PA equals LU. Master that, and the same tired system will never cost you twice.